So welcome to our last section in Chapter 8, where we're going to be looking at improper integrals. The definite integrals we have encountered so far involve finite valued functions and finite intervals of integration. In this section, you will see that definite integrals can sometimes be evaluated when these conditions are not met. Let's look at an example. The energy required to launch a rocket from the surface of the Earth, with the Earth radius equal uppercase R, to an altitude of h, is given by the integral from r to r plus h of k over x squared dx, where k is a constant that includes the mass of the rocket and of the Earth, and the gravitational constant. This integral may be evaluated for any finite altitude where h is greater than 0. Now suppose the aim is to launch the rocket to an arbitrarily large altitude h so that it escapes Earth's gravitational field. The energy required is given by the preceding integral as h approaches infinity, which we write the integral from r to infinity of k over x squared dx. This integral is an example of an improper integral, and it does have a finite value, which explains why it is possible to launch rockets to outer space. For historical reasons, the term improper integral is used for cases in which we have one of two conditions. First of all, the integral of integration is infinite, and that's what we saw in the last case where we were integrating from r to infinity. So the interval of integration, the limits, are infinite. And the second is when the integrand itself is unbounded on the interval of integration. So if we're looking at an integral between a and b, somewhere between a and b, the function itself is unbounded. It goes to infinity or negative infinity. So let's look at an illustration or a simple example of an infinite integral. Consider the integral from 1 to b of 1 over x squared dx for any real number b greater than 1. And so what we can see by looking at the diagram here is that what we're talking about is the area under the curve from 1 to whatever the value of b that we assign. Okay? If we continue to allow this to go to infinity, we can see that the area, while it's not really finite, it is to a certain degree finite because we're getting closer and closer to 0. Okay, so let's look at this integral and see what happens. So if we integrate from 1 to b of 1 over x squared dx, the integral of 1 over x squared is negative 1 over x, and of course we're evaluating that from the values of 1 to this arbitrary value or assigned value of b. And so we get 1 minus 1 over b. If we want to know, for example, if b equals 2, then from 1 to 2, the area is 1 minus 1 over 2, or 1/2, so we get an area of 1/2. If we go from 1 to 3, if we make b equal 3, so you got these kind of arbitrary or assigned values there, we get 1 minus 1 over 3, or 1 minus 1/3 is 2/3. And so, it's very intuitive. You can see from the diagram, as b increases, of course, the area increases because we're adding extra sections. But what happens if we do want to figure out what's happening as b goes to infinity? Well, we can apply the limit on the integral as b goes to infinity, which is really the same thing as changing b to infinity, which we could do there. Or we could put the limit as b goes to infinity on our result of the original integral from 1 to b. And so we can apply the limit to the result of our integration. And of course, as b goes to infinity, 1 over infinity goes to 0, so our value just is equal to 1. So we can use this concept of limits to kind of sort out what's happening as we're integrating over an infinite interval, as you can see here in the white. And this, of course, is one of the conditions of it being a an improper integral. So now let's look at one of those conditions of improper integrals, specifically when you're integrating over an infinite interval. Like we just saw in the last case, we had a condition where the function was continuous from a constant value all the way to positive infinity. Here, what we were technically doing is integrating from that value of a to infinity of a function. And we did that by integrating from a to b, and applying a limit as b goes to infinity of f of x dx. And that's how we actually solved the last problem. And so this is giving you kind of a hint of how we're going to do analysis on these infinite interval improper integrals. So the second case is when we have really just the flip diagram here, and we can see that the function is continuous from negative infinity to some value of x here at b. And so technically what we're doing is we're integrating from negative infinity to b of f of x. And so here we're just going to apply the limit as a, the lower interval value a, goes to negative infinity of the integral from a to b f of x dx. And then the last case is when you have a function that's continuous from negative infinity to positive infinity. And here what we're going to do is we're going to use the idea that the sum of two integrals is equal to the integral of a sum. And so what we're going to do is take the integral. What we're actually doing is separating the integral from negative infinity to infinity, from negative infinity to a chosen point, and then from that chosen point to infinity. Notice that this midpoint of the value c needs to occur in both integrals. And it can be shown that the choice of c does not affect the value or the convergence of the original integral. And so we have these three different kind of infinite intervals that we're going to solve in similar ways, as you saw in the example we just did, by flipping that limit or by making it a sum of two limits. If any of these limits exist, then the diagrams that you see here would be representative that all of the functions are converging. If there is not a value that exists, then the integrals diverge. So let's try our first example, example 1a. Evaluate the integral from 0 to infinity of e to the negative x dx. This is very similar to the illustration that we did, and it's also the first case in the three different cases we just looked at. So hit pause and see if you can evaluate this integral by applying the limit to the solution for the definite integral. So hit pause and try now. So if we're integrating from 0 to infinity of e to the negative x dx, what we're going to do is integrate from 0 to b and apply the limit as b goes to infinity of e to the negative x dx. Of course, the integral of e to the negative x is negative e to the negative x, evaluated from 0 to b, which we're going to apply the limit. If we evaluate this from 0 to b, we get e to the negative 0, or e to the 0, which is 1, and e to the negative b. Okay, notice this flips around because this is e to the negative b minus 1, but it's minus a negative 1, so they put that first. So it's negative e to the negative b minus a negative 1, which is of course plus 1, and so that's just flipped. Okay, so don't get confused by how they flip the directions here. And then of course, as we apply the limit as b goes to infinity, well, e to the negative b is 1 over e to the b. E to the infinity is infinity, and 1 over infinity equals 0, and so we just get the value of 1. So let's try a more complicated example, and I really want you to try this on your own, at least the setup, okay? Now, here we're evaluating example 1b, we're evaluating from negative infinity to infinity of dx over 1 plus x squared. This is a simple integral using your table of integral values. But remember that when we're evaluating from negative infinity to infinity, what we're doing is we're actually going to evaluate the sum of two integrals, and so we have to pick an arbitrary value in the middle. So even if you can't solve this entire integral, which you should be able to do, try at least to set up that sum and see if you can apply, remember how to set up the sum to go from negative infinity to a value plus another integral from that same x value to positive infinity. Okay, so try that now. Hit pause, set it up, and then see if you can solve it. This is a pretty straightforward integral, and you've actually got the answer right here in your diagram in the graph, which should be the value pi. So if we choose c to be 0, and generally this is probably the best value to pick, not always, because 0 is usually an easy value to calculate, okay? Not always true, but so here we have the integral as a goes to negative infinity from a to c of the integral, plus the limit as b goes to infinity from c to b, okay? And here we're going to set c equals 0. Again, this is probably the typical value we're going to set for when we go from negative infinity to positive infinity. Not always, but in general, that's a good value to calculate because 0 values are easier. A lot of times the functional value goes away when x is 0. So the integral of 1 over 1 plus x squared is inverse tangent. So we're evaluating the limit of inverse tangent of x between a and 0 as a goes to negative infinity. And then we're doing this plus adding the integral, or adding the limit as b goes to infinity of inverse tangent evaluated from 0 to b. So here we have the tangent of 0 is 0 minus the inverse tangent of a, the inverse tangent of 0 is 0 minus the inverse tangent of a, plus the limit as b goes to infinity of the inverse tangent of b minus, again, the inverse tangent of 0 is 0. Okay? When we apply these values, we get the inverse the inverse tangent of negative infinity is negative pi over 2, and the inverse tangent of infinity is pi over 2. And so these are the values where we have asymptotes for tangent. And so pi over 2 plus pi over 2 equals pi. So let's look at example 2. And specifically, we're looking at a family of function values, f of x equals 1 over x to the p, where p is a constant or any real number. Example 2, for what values of the real number p does the integral from 1 to infinity of 1 over x sub b dx converge? So this not only takes the analysis, but it also takes some critical thinking. A lot of times when you get problems like this, we get stuck because we're not exactly sure. We may know how to solve this for a specific value, but we're not really sure how to answer this question. So my advice is go ahead and start with what you know. So the first thing we can do is certainly to solve this based upon the analysis tools by applying the limit. So hit pause and see if you can set this up and see if you can solve for the first integral. And then we can, that will have a variable of p in it as part of your solution. So hit pause and see if you can set it up and see if you can solve it to have a solution with p in there. So if we take the limit from 1 to infinity, of course this is the limit from 1 to b, applying the limit as b goes to infinity of x to the negative p. Now remember, p is a constant, so this is just like any power. So the integral of anything to the power is 1 over the exponent plus 1 and the new exponent is the old exponent plus 1. Well, negative p plus 1 is the same as 1 minus p, so that's why you see this coefficient in front and why they've made it 1 minus p, because negative p plus 1 is the same. And here we are applying the limit. Well, 1 over 1 minus p is a constant, so we can pull that out in front. When we apply the limits of integration, we get, we plug in b for x, we get b to the 1 minus p minus 1 to the 1 minus p. Well, 1 to any power, even if it's 1 minus p, is going to be 1. And so that's why you don't see the exponent there. So we have a solution here, and now we have to kind of use critical thinking to kind of figure out what happens in each, when, for what value of p is this going to increase or decrease, or excuse me, converge to a constant or diverge to, just a large number. So since we're looking at p, 1 minus p in the denominator, let's look at values at 3 different cases, when p is greater than 1, when p is less than 1, and when p actually equals 1. In the first case, if p is greater than 1, then p minus 1 is going to be greater than 0. P minus 1 is going to be greater than 0. And b to the 1 minus p is going to equal 1 over b to the p minus 1, right? Because 1 minus p is going to be a negative number, and that negative number is going to be equal to p minus 1. So we can see this is 1 over b to the p minus 1. And of course, as b goes to infinity, then 1 over infinity goes to 0. Okay? So this number here approaches 0, and then we just get a solution of 1 over 1 minus p, or excuse me, 1 over p minus 1, because we're multiplying it by negative 1 there. And of course, this is a constant, so this converges. So if p is greater than 1, we have a convergence. What happens if p is less than 1? This is case 2. If p is less than 1, then 1 minus p is positive, and we have the following. So 1 minus p is positive, so b to the 1 minus p is b to a positive number. If b is infinity to a positive number, even if it's a fraction, like 1/2, the square root of infinity is still considered infinity. So we have infinity minus 1, which is still infinity. And so here we have the answer of infinity, which means it's not converging to a constant or a specific finite number. So in this case, case 2, the integral diverges. The last cases we have to consider is if p equals 1. Well, notice if p equals 1, then we simply get the integral of 1 over x. Well, the integral of 1 over x changes all of this, because the integral of 1 over x is simply the natural log of x. Okay? Well, here all we have to do is apply the natural log of, apply the limit as b goes to infinity of the natural log of b, right? So, and this of course equals infinity, so the integral diverges. I mean, you could put in the natural log of 1, which is 0 too, but so you have infinity minus 0. All right, and then if you want to kind of see these cases, you can see a case there where p is greater than 1, p is less than 1, and p equals 1 in this diagram here. Next, we're going to look at example 3, and we're going to have 3 different questions about this. So we're first looking at example 3a. Let R be the region bounded by the graph of y equals x to the negative 1, which of course is just 1 over x, and the x-axis for x is greater than or equal to 1. Example 3a. What is the volume of the solid generated when R is revolved around the x-axis? Hit pause and see if you can do this. This takes us directly back to section 6, chapter 6, when we did solids of revolution. And so think about which method do you need to use. Often it helps if you think about, if you draw the diagram and can visualize what's going on. So here we have the graph of 1 over x. If we revolve it around the x-axis, we can see the shape that we have here, which kind of looks like a megaphone or funnel, etc. And so do you know which method you would use here? Well, there's not a hole in the middle, so we're going to have circles or discs that we're going to use all along. So try using the disc method and then set up this integral, and it's not really that challenging of an integral to solve, even though it's an improper integral. So try that, hit pause, and see if you can solve this using the disc method. So remember, the disc method is we're doing the area of each circle, which is pi r squared, where the radius is actually the function. We're evaluating it from 1 to infinity because we have x is greater than or equal to 1, so it's going on to infinity. So we have the volume equals the integral from 1 to infinity of pi f of x squared, which is, of course, when we apply our analysis, the limit, we pull the constant pi out front. The limit is b goes to infinity of 1 to b, the integral from 1 to b of 1 over x squared. This simplifies to pi times the limit of b over infinity, and I'm not going to walk through the steps. This is a simple integral to solve, of 1 minus 1 over b. And of course, as b goes to infinity, this second term goes to 0, so we just get pi times 1, or pi. All right? So let's look at 3b next. So let's look at example 3b. What is the surface area of the solid generated when R is revolved around the x-axis? Do you remember the formula for surface area from section 6.6? The surface area is the integral from 1 to b of 2 pi f of x times the square root of 1 plus the derivative of f of x squared. So if we plug this into our formula, and again, I encourage you to hit pause, not pi, hit pause here and try to do this, but I will warn you that this one takes some critical thinking again to solve this problem versus a strict analytical method to solve the integral. So if we plug this into the surface area formula where our f of x is 1 over x and our derivative of 1 over x is negative 1 over x squared, we end up with this final integral 2 pi times the limit as b goes to infinity from 1 to b of 1 over x cubed times the square root of 1 plus x to the 4th. This is a bit of a complicated integral here where if we do some thinking about this, it's much easier to solve thoughtfully than analytically. And what I mean by that is when we look at this last integral, notice if what we had under the square root was just x to the 4th, this would be a greatly simplified integrand. We'd simply have the square root of x to the 4th over, which is x squared over x cubed, which would just give us the integral of 1 over x. Well, let's think about that. Since we're on we have all values of x greater than or equal to 1, then we know that every case when x is greater than or equal to 1, the square root of 1 plus x to the 4th is going to be greater than x to the 4th. I mean, that's just common knowledge. Okay, and of course the square root of x to the 4th is x squared. So we get that our integrand is always going to be greater than this simplified integrand of 1 over x. So we know that the surface area formula is going to be greater than 2 pi times the integral of this simpler integrand. So our value from our formula is going to be greater than this value, which is easier to solve. And in fact, we did solve it in example 2, and it equals infinity. So if this smaller value is infinity, then we know, in fact, that our larger value is infinity as well. And so in this case, this integral diverges. It does not converge to a number, which when you think about it is quite interesting, because in 3a, we said that the volume converges to a specific finite value, whereas the surface area does not. It just keeps growing. So it's a bit confusing from a logical perspective to really think about and get our hands around that the volume could be finite while the surface area is infinite. This also is a challenge of problems like this, because here again, there's, a lot of times in math we look for specific rules. When A happens, do this. When B happens, do this. But sometimes you have to step back and look at things, like in this case, this is such an easier integral to solve if we can think about the relationship between the integral we have and a much simpler integral here, and just in terms of value. It makes our solution much easier to find. So we've been at this a while now. We've probably been at it for about 25 minutes, and we're about the halfway point of this lecture. It's quite a long one, and so it's really a good idea to give your brain a break. Get up, walk around, step outside, take a walk, get a drink. Just stop for a few minutes what you're doing and kind of refresh. It actually helps for your studying habits, I think, to get out of, it's kind of like giving your brain a shower. Sometimes just doing something different. If there's like a crossword puzzle or something you like to do, I play a little game on my phone called Idiot, which is just like a solitaire game, and it only takes 2 or 3 minutes per hand, and it just kind of allows me not to think at all for a few minutes. But I've given you another question here, and this really is personal to me. I did a lot of thinking throughout my career of what I wanted to do, and although often I fell into different jobs by opportunity and by promotion. But most of us have probably given a lot of thought to what we want to do for work, especially if you're in Calculus 2, you already have committed to, some course of action that's along technology or STEM, etc. But have you ever really thought about where you want to do it? And this is a question I'm really, one of my regrets is that I followed jobs and I moved around the country. I even moved around the world, less as a conscious thought than as an opportunity. I kind of followed jobs, which wasn't necessarily bad early in my career. I went to school in upstate New York, and then my first real job after college, took me to North Carolina. Within a few months, it took me to Florida. It put me out here in Dallas for one summer for a temporary assignment, then back to Florida, and then a promotion brought me back to Dallas. Eventually, later on, I was looking for work in Dallas and found a role in Germany, which was an exciting opportunity for me because I had always wanted to live and work outside the U.S. But now, as I'm nearing retirement, I realize there are things that I really enjoy in my life outside of work, namely hiking and doing outdoor things, that the majority of my career has been spent in Dallas, which doesn't have the best geography for that. And had I thought about that 20 years ago, 30 years ago, I certainly could have found jobs that were similar to what I was doing in a location and that I might have preferred much more, and would have, preferred to be buying a house in that place so that it's paid off when I retire, etc. And several people I know recently have been thinking about this and talking about it, that they really want to live someplace pretty, and they're wondering why they decided to wait till they retire. So it's just a thought, maybe think about some places you want to live, and maybe even as you go through your career, when you take vacations, don't just take vacations maybe to go to Hawaii or something, or maybe that is where, but think about maybe there are some spots that you might think about living in permanently. And so take a vacation there and get a taste of it, etc. So anyway, just some food for thought. Take a break as long as you want, hit pause, and then continue on for the rest of this lecture. Sorry it's a long one, folks, but that's why I give you these breaks or suggest these breaks. So let's look at the last example, 3C. In this case, we're going to use the same formula, but we're going to try to find the volume of the solid generated when R is revolved around the y-axis. Again, it helps us to look at a graph of this, and we can see that we have a couple different methodologies we could use here. Do you remember what they are? Hit pause if you do and see if you can solve this. Okay, this is again from section 6. By looking at this, you could see that there's two different methods. I can see that I could evaluate this as a disk, but not really a disk, but a washer, because there's a hollow in the middle, because we go from 1 to infinity here. So we could use the washer method, or we could also use the shell method. And what I'd like you to do is to use the shell method from section 6.4. That's what I'm going to use. Actually, you can use either method and you should come up with the same answer. Do you recall the formula for the shell method? The volume is equal to the integral from x equals a to x equals b of 2 pi x times f of x dx. So now you have the formula for the shell method. You've got a simple formula here. This is a very simple integral to solve, so if you haven't hit pause yet, I suggest you do it now and try to work this out. The more that you do on your own while I'm going through these, the better off you are. I mean, I have the same problem when I watch something that I think, oh, that was easy, and I overestimate my ability or my recall of that, and when I go back to it later, I realize that it's not quite as easy as it looked. Okay, so anyway, here's our integral. If we plug in the value of f of x as 1 over x times x, then notice what we get is a simple integral of 1, because 1 over x times the x in our formula just gives us 1. And so this becomes a simple integral to solve, and we can see here that as b goes to infinity, the answer goes to infinity as well. So in this case, the volume diverges, and there is no finite volume for this figure. And it may be, conceptually, this doesn't. Actually, that's not true. What I was going to say, I was thinking that this was yeah, it does. What am I saying? That this whole is going to be constant there, so this is not ever going to get to 0, even though that function does. We're only evaluating it from 1 to infinity this way. Okay? So now let's look at the other case of improper integrals, specifically when the integrands are unbounded. Improper integrals also occur when the integrand becomes infinite somewhere on the interval of integration. So let's look at a function, f of x equals 1 over the square root of x, specifically between x equals 0 and x equals 1. If we wanted to figure out that area, notice that f is not defined at 0 because we'd have 1 over the square root of 0 or 1 over 0, which is undefined. And also as notice that f goes to infinity as x approaches 0 from the positive direction. So we're going to set this up very similarly that we would do with the other functions. So notice here we're undefined. The integral from 0 to 1 of 1 over square root of x is undefined at 0. So what we're going to do there is replace that 0, that undefined value, with again an arbitrary value of c, as you can see in the diagram, and then use a limit function as c approaches 0 from the positive direction. As we do that, notice the integral of 1 over the square root of x gives us 2 times the square root of x. And again, we're going to evaluate that from c to 1, and we're going to apply the limit as c approaches 0 from the positive direction. Well, when we plug in these values, we get 2 times the square root of 1 minus 2 times the square root of c, or simply 2 times the quantity of 1 minus the square root of c. Well, if we plug in 0 for c, then of course this term disappears, and we get just 2. And so our area under the curve between 0 and 1 is equal to 2, which again is another weird answer, because we have a finite area under an infinite curve, that this curve keeps going on up to y equals infinity. So again, another kind of strange and counterintuitive idea. Next, we're going to look at improper integrals, specifically the ones that have unbounded integrands, and we're going to find that we're going to handle this pretty similarly that we did when the limits were unbounded. So let's look at the three cases here. If we have a function that's continuous over the interval a, b, and notice here that it does not include a, but it starts at a, and that's because the limit as x approaches a from the positive direction, the function value is going to positive or negative infinity. So specifically what we have here is an asymptote at x equals a. And so we're going to handle this very similarly. Because there's really no value at a, the integral from a to b of f of x dx we're going to handle with a limit. We're going to have the limit as c approaches a from the positive direction of the integral from c to b of f of x dx, as you can see here. If we have the opposite situation where the function, sorry, I went blank. If it's continuous from a to b but doesn't include b, and as the limit as x goes to b from the negative direction of f of x equals positive or negative infinity, it's really the same situation here, right? Except where the upper limit is now our asymptote. So here we're going to have the limit as c goes to b from the negative direction, and we're going to replace b as the upper limit with c. So these are pretty similar to what we did before. They're very intuitive of where is the asymptote. If it's at the right end, then of course it's going to be the upper limit, and if it's at the left end of the graph, then it's going to be the lower limit, etc. And then similarly, we might have a function that is continuous over all AB. However, at some interior point P, it's unbounded, and you can see a good diagram here. And again, we're going to handle this in a similar way, where we're going to do the sum of two integrals from a to c, where c is approaching p from the negative, plus the integral from d to b, and again where d is approaching p from the positive direction of f of x dx. Now here you see that we have different values, because we're talking about being on opposite sides of the asymptote. But notice that both of these are approaching by using the limit. They're both going to the value of p, just from the opposite direction. And again, similarly to what we saw before, if the limit exists, then the integrals converge, and if the limit doesn't exist, then the functions diverge. So let's look at our next example for an infinite integrand from example 4. Find the area of region R, the region between the graph of f of x equals 1 over 9 minus x squared, and the x-axis on the interval -3, 3 if it exists. So we can see here that this is a symmetrical function around the y-axis. So the area between -3 and 0 is equal to the area from 0 to 3. So the first thing we can do is rewrite the integral from -3 to 3 as 2 times the integral from 0 to 3 of 1 over the square root of 9 minus x squared, which of course is our f of x function. Okay? But here we know that at the value of 3, we have an asymptote. So this is where we're going to assign that value of a variable to replace the upper limit and then apply a limit against that. So here we're going to replace 3 with a variable c and then use the limit, since we're going from 0 to 3, as c approaches 3 from the negative direction. Here we have a simple integral, which is the inverse sine of x over 3. And so we're going to evaluate that from 0 to c. So this gives us 2 times the limit as c approaches 3 from the negative direction. And so we get the inverse sine of c over 3. Well, of course, this becomes the inverse sine of 1, which is 90 degrees or pi over 2, minus the inverse sine of 0. And of course, sine is 0 at 0. This then gives us the integral of 2 times pi over 2 minus 0, or pi. So our area is equal to pi units. This one was pretty straightforward. Again, what you're trying to realize is think about the limits on your integral, and specifically where are those limits becoming asymptotes or going to infinity, or they don't actually exist. If we plug 3 or -3 in here, we get 0 in the denominator, and that's why we know that those don't exist. So now let's look at example 5, and this is when we have an infinite integrand at some interior point. Let's look at the example. Example 5, evaluate the integral from 1 to 10 of dx over x minus 2 to the 1/3 power. Well, immediately we can see that x minus 2 in the denominator is going to give us an undefined value at x equals 2, which is an interior point for this integral. So we know that we're going to have the undefined points in the middle. So this is the case where we have a sum of 2 integrals. So see if you can set up the integral as the sum of 2 before you move on. And if you can do that, then this is quite an easy integral to solve. This is a simple substitution with u equals x minus 2. So hit pause and see if you can first set up the integral sum. That's the next slide I'm going to show you, or the next piece that's going to be added here. So first set it up, and then you can hit play and check your integral setup, and then see if you can solve it. So again, we're going to be looking for the integral from 1 to 2, plus the integral from 2 to 10. So we have the integral from 1 to 2, and then the integral from 2 to 10. But of course, we know that at 2 it's undefined, so that's where we're going to apply the limits. As we're going from 1 to 2, this is the upper limit, so we're going to approach the limit as c approaches 2 from the negative direction. You can see that there. And then the second integral is the lower limit, and so here we're going to approach d equals 2 from the positive direction. So these are important, and they're quite intuitive again. All right. So once you have this down, then it's quite easy. Both the solutions to both of these integrals are the same, and then we just have limits from 1 to c, and then from d to 10, where we have approaching different values of the limit, or the one-sided limits. Okay. So here, the integral of 1 over x minus 2 to the 1/3 is 3/2 x minus 2 to the 2/3. This is a simple power rule with substitution, evaluated from 1 to c. Plus the integral as d goes to positive 2 of that same indefinite integral from d to 10. When we plug all these in, I'm not going to go through these steps. We get the limit as c goes to 2 to the negative direction of c minus 2 2/3 minus 1 minus 2 to the 2/3. And again, plugging in all these values, plus the second integral, 3/2 times the values of 10 minus 2 to the 2/3 minus the limit as d goes to 2 positive of 2 minus 2/3. Okay, so this first, the limit on c at 2 minus 2 is 0, so we get 0 minus the second part of the integral, and the limit in the second integral, the second part, the second term goes to 0 because 2 minus 2 is 0, which you can see there. And now it's just making the math, the arithmetic, and we ultimately get 9/2 for the area of this evaluation, of this integral, the solution to this integral. So our last concept from Chapter 8 is the comparison test. And there's some cases in which we cannot determine whether a given improper integral converges or not, simply because it's impossible to compute an antiderivative using the catalog of integrals that we've had, or any of the methods that we have. So we can use something called the comparison test. Suppose that functions f and g are continuous on the interval from a to infinity, with f of x greater than or equal to g of x, which is greater than or equal to 0 for all of x greater than or equal to a. So the key part here is f is the larger function, and then g of x, f of x has larger values than g of x over the entire interval. So if f of x, the larger function, converges, then of course the smaller function converges, because if f of x goes to some constant, say 2, then we know that g of x has to go to a value that's 2 or less. And by corollary, the opposite effects. If the smaller function diverges, then the larger function diverges. And that's all the comparison test is saying. So if you have a function that you're trying to figure out whether it's converging or diverging, if you can simplify that function to where you can find a solution, and if you can compare the values and know that one is larger or one is smaller over the entire interval, then you can use the convergence test. Again, if the large function converges, then the small one does. If the small function diverges, then the large one does. Okay? And again, that's pretty intuitive. So let's look at an example for the comparison test. Example of 7a. Does the integral from 1 to infinity of e to the negative x squared dx converge? Well, if you remember from example 1a, we saw that e to the negative x from 0 to infinity dx was equal to 1. So this integral converges. However, we're looking to integrate from 1 to infinity. But if from 0 to infinity, and we remember that an integral equals the area under the curve, then from 1 to infinity of e to the negative x would be even less than 1. So this also converges. If we then think about how e to the negative x and e to the negative x squared compare for values of x greater than or equal to 1, well, e to the negative x equals 1 over e to the x. And if we're looking at values of 1, when they're 1, e to the x is 1 over e to the x is 1 over 1, which is 1. 1 squared is also 1, so we get 1 over 1 again, or 1 over e to the 1. So I said e to the 1 was 1, and that's not true. We get 1 over e, which is equal to 1 over e. If we go to 2, then if x is 2, for example, we get 1 over e squared. But here we get 1 over e to the power of 2 squared, e to the 4th. And because this is in the denominator, this is going to be a larger value. E to the 4th is larger than e squared. So 1 over a smaller number is, as a fraction, when the denominator is larger than e to the negative x, is going to be greater than or equal to e to the negative x squared for all values of x greater than or equal to 1. Thereby, we can say that using the theorem 2, since e to the x converges, then e to the negative x squared over that same interval is going to converge. And here you can actually see the graphs of both e to the negative x squared in green and then e to the negative x in blue. And you can see that, as we said, right at 1, they converge. And in this case, had we tried to do this from 0 to infinity, it would have been much more difficult because the functions aren't in the same relationship, larger and smaller, over that entire interval from 0 to infinity. But from 1 to infinity, they indeed are. You can see that from 0 to 1, e to the negative x is actually less than e to the negative x squared. And that's because of its being a fraction. And then, of course, once we hit 1, then they flip-flop with e to the negative x being greater than for the rest of the values. Let's look at our last example in Chapter 8, example 7b. Does the integral from 1 to infinity of 1 over the cube root of x squared minus 0.5 dx converge? The challenge with most of these comparison problems using the comparison test, Theorem 8.2, is finding a similar function that we want to compare it to, a simpler function. So often we're looking at the original integrand and trying to simplify it. So if we take the minus 0.05 out of the denominator, then we're comparing 1 over the original function, cube root of x squared minus 0.05, to 1 over the cube root of just x squared. And then trying to figure out if this is larger or smaller for positive values greater than 1. So just put something in there. Let's put x equals 2. You get 2 squared is 4 minus a half is 3.5 over the cube root of 2 squared, 4. Okay, so we can see here that 3.5 is less than 4, but remember we're in the denominator here. So remember, when the denominator is smaller, the actual entire fraction is bigger. For example, 1/2 is greater than 1/4. So we can see that this function, our original function, is greater than 1 over the cube root of x squared, which we could simplify to 1 over x to the power of 2/3. Now, if you remember back to example 2, we actually did a similar problem where we did 1 over x to the power of p, and then we considered where it converged and where it diverged. Okay? So in this case, when p was less than 1, that function diverged. And since this is the smaller function, then of course the larger function is also going to diverge. All right, so this is the end of Chapter 8. We're now getting ready to take our next test, which covers all 9 sections of Chapter 8. This is a lot of material we covered, and so really be practicing as many problems as possible and doing extra problems in the book, and then using whatever resources you can.